Hello everyone. Welcome in the last session of the matrices, Cayley-Hamilton theorem. Okay, so it is the name of a scientist, Cayley-Hamilton. So, and the Cayley-Hamilton theorem, the statement of the theorem is every square matrix satisfies its own characteristic equation. Okay, every square matrix satisfies its own characteristic equation. That is a statement by Cayley-Hamilton. So just we have to check this for any square matrix. That square matrix A itself satisfies the determinant A minus lambda I equal to 0. So generally we get a characteristic equation in terms of a lambda. So if we replace that lambda by A, then also the matrix equation is valid there. That we have to prove here. And the use of Cayley-Hamilton theorem is to find out inverse of a matrix or higher powers of the matrices that can be obtained with the help of Cayley-Hamilton. We'll see one example here. Suppose our aim is to check whether this matrix A satisfies Cayley-Hamilton theorems. We have to verify indirectly. Okay, verify this matrix A satisfies the Cayley-Hamilton theorem. Also, we have to find the inverse of a matrix. So, what is step number one? Step number one, we should consider characteristic equation which is determinant A minus lambda I of 0. So, already we learned the shortcut method for getting this characteristic equation. It is a lambda cube minus sum of diagonal element 2 plus 2 plus 2, that is 2 plus 2 plus 2 into lambda square plus sum of the minor of a diagonal element. If I take a minor of a11, it is 2 2s are 4, 4 minus 1 is a 3. So this is m11. Let us take minor of a22 now. So 2 2s are 4, 4 minus 1, that is also 3. And minor of a33, 2 2s are 4 minus 1, that is also 3. See, lambda cube minus sum of diagonal elements into lambda square plus sum of a minor of a diagonal element into lambda minus determinant of A. Now to take a determinant, so 2 into its minor, so already we calculated that minor is a 3, minus minus plus 1 now, and minor of this A12, this is a minus 2, this is minus 2 uh, plus 1, minus 2 plus 1 is a minus 1, is it? Plus 1, this plus 1 last, and this is a 1 minus 2, 1 minus 2 is a minus 1. So that about a determinant is equal to 0, is equal to 0. So we get here a cubic equation, lambda cube as it is, sum of a diagonal element is a 6 minus 6 lambda square. This sum of a minor is a 9, 9 lambda, 9 lambda, and let us check this determinant value now. This is 6 minus 2. 6 minus 2 is a 4, so it's a minus 4 equal to 0. So step number 1, we should get this characteristic equation. This is the characteristic equation for the matrix A. This is the cubic equation. And what is our aim? What is the statement says? Cayley-Hamilton states that this equation is satisfied by the matrix A. Now we have to verify. We have to verify A cube minus 6a square plus 9a, constant will be replaced by 4 into I, because identity element in the matrix equation is I, not a number 1. So this is the equation that we have to verify. Our aim is to prove, our aim is to verify the sum of these four quantities, a cube, 6a square, 9a, 4i. If we add like this, it should come as a 0. So that is a Cayley-Hamilton equation. This is the equation we get because of this Cayley-Hamilton only. So I will show you the same thing here, the step number 1, that what we done here. So we got this equation, lambda cube minus 6 lambda square plus 9 lambda minus 4. So what we require now, we have to calculate a square and a cube. Okay, so this is just a calculative. So let me move to the a square. How to get a square? A into a. Just we have to multiply the matrix A with the matrix same again. So here is a square. How we got this a square? You will observe. Just we taken the a into a. So first row with the first column. So 2 2s are 4. 4 plus 1 plus 1, that is 6. We got first row, first column, that is a 6, because 4 plus 1 plus 1. first row, second column, if you go first row to the second column, this is minus 2, minus 2, minus 2, and minus 1. So minus 2, minus 2, minus 1 become minus 5. That is first row, second column. And lastly, first row, third column, which gives you 2 plus 1 plus 2. Okay, and that is a 5. So like that, now we'll move to the second row. The second row gives you the elements here, and the last row gives is here. So step by step, we have to do this calculation. So we get that a square here. After a square, we want a cube now. How to get a matrix a cube now? To get a cube, just a square into a or a into a square. Both way it is okay. So choice is your. So here I done a cube is equal to a square into a. So here is a matrix A square and this is a A. Again this row by column multiplication, and we got A cube. Now just start with the LHS. See, A cube is available, A square is A cube and A square we calculated, A is already given, and identity matrix we require. All these things we have to replace in the LHS, and we should say directly 0 also, because it is a theorem, it is a universal truth. It should come as a 0, and our aim is to just verify only. So we'll start with the LHS. The LHS is consider A cube minus 6A square plus 9A minus 4I equal to, this is the value of A cube, minus 6 times A square plus 9 times A minus 4I. And what should be our answer? The answer should be equal to 0. So you can write down directly also 0 there. So this is the 0. And just say, hence Cayley-Hamilton theorem verified. Hence the Cayley-Hamilton theorem verified. So that is the first part of the question. Now, with the help of this equation, we can find out the inverse of a matrix or higher power. So if you want the inverse of a matrix, multiply to this matrix equation by A inverse on the both side. If you want the value of A raised to 4, multiply this by A to the both side, that way. So come to the next part. So to find the inverse of a matrix, yes, we are going to multiply by A inverse on the both side of this matrix equation. So if you multiply by A inverse, so remember A inverse into A is I. So when you multiply A inverse into A cube, it is like it left only A square, because 3 minus 1, the power of A left A square, minus 6A, 9A into A inverse, 9I, and here is a 4A inverse, and that will be the next step. So when you take this A inverse inside the bracket, we are getting this equation. Okay, and now just we rearrange this equation to get the value of A inverse. So 4A inverse we take on the other side, and we get 4A inverse equal to A square minus 6A plus 9. So what is the formula for A inverse? A inverse becomes 1 by 4 times A square minus 6A plus 9. And see, A square value is already we calculated, A is known and identity. So if we replace all these values and just do the addition, just we add these three terms, we get the required answer. So this is 1 by 4, this is the value of A square, value of A, this is the identity matrix. Just multiply the scalar inside first and take the sum of the corresponding compounds, sum of the subtraction. Here we have to subtract it, here you have to add it. Okay, so if you do this part, yes, we get a inverse. So this is the another way to get the inverse of a matrix. So there are a number of ways of getting the inverse. You may already learned adjoint method, but yes, Cayley-Hamilton theorem also can be used to get the inverse of a matrix. By chance, suppose in the question we have to find out A raised to 4. We have to find out A raised to 4. What will we do it? Multiply both sides of this equation by A. So we get A cube into A is A raised to 4 minus 6A cube plus 9A square minus 4A equal to 0, because we multiplied by A. So we get a formula for A raised to 4. A raised to 4 becomes 6A cube minus 9A square plus 4A. Now see the previous step, we already calculated these values. A cube value is already available, A square is also available, A is only given. We can replace all these values and we can add these three matrices and we get A raised to 4. So either we have to find out higher powers of A or A inverse. Yes, we can use Cayley-Hamilton theorem. That about the Cayley-Hamilton theorem and its statement. So maximum 2 types of questions will come. You have to verify Cayley-Hamilton for 2 by 2 matrix or 3 by 3 matrix. Okay, so 2 by 2 is very simple because you get a quadratic equation and you just calculate A square there. Okay, so I will give the 2 by 2 examples as exercise. Do it your own, try it your own. Okay, so that about our last article, Cayley-Hamilton theorem. Okay, thank you.